In the early hours of March 5, 1979, something happened that would change our understanding of the universe forever. At exactly 10:51 Universal Time, every satellite orbiting Earth suddenly went haywire. Soviet Venera probes near Venus registered impossible radiation spikes. American satellites monitoring for nuclear launches began screaming warnings. Deep space probes billions of kilometers away detected the same anomaly at the exact same moment. For a few terrifying minutes, military officials on both sides of the Cold War stared at their screens in confusion and growing panic. The radiation signatures looked like nothing they had ever seen. It wasn't coming from Earth. It wasn't coming from the Sun. It was coming from everywhere at once, as if the entire solar system had been plunged into an invisible sea of gamma rays. Soviet scientists frantically called their American counterparts on the nuclear hotline. This wasn't an attack. This was something else. Something far more terrifying than any weapon humanity had ever conceived. Within hours, astronomers around the world had triangulated the source. The radiation burst had originated from a point in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way. The distance? 150,000 light-years. Let that sink in for a moment. An explosion so powerful that it traveled across 150,000 light-years of empty space and still had enough energy to disrupt technology throughout our entire solar system. An explosion that happened when our ancestors were just beginning to walk upright in Africa, its light only now reaching us with enough force to overwhelm our satellites. This was humanity's first encounter with what would later be called a magnetar, and we had no idea what we were dealing with. To understand magnetars, we first need to understand their slightly less terrifying cousins, neutron stars. When a massive star runs out of fuel, its core collapses in on itself in a catastrophic implosion. The outer layers rebound and explode outward in what we call a supernova, one of the most energetic events in the universe. But the core? The core keeps collapsing. Electrons are crushed into protons, creating neutrons. The entire mass of a star's core, roughly 1.5 times the mass of our Sun, gets compressed into a sphere about 20 kilometers across. That's roughly the size of Manhattan. A single teaspoon of neutron star material would weigh about 1 billion tons. That's roughly the mass of Mount Everest, compressed into something you could hold in your hand if your hand could somehow avoid being instantly vaporized by the encounter. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's. If you somehow stood on the surface, you would be flattened to a thickness of a few atoms. The escape velocity is roughly 1/3 the speed of light. These objects represent matter compressed to the absolute limit of what physics allows before it collapses into a black hole. But neutron stars, terrifying as they are, pale in comparison to magnetars. In 1992, two physicists named Robert Duncan and Christopher Thompson published a paper that most of the astronomical community dismissed as science fiction. They proposed that some neutron stars, under very specific conditions during their formation, could generate magnetic fields so powerful they violated everything we thought we knew about the limits of magnetism. We're not talking about magnetic fields a little bit stronger than normal neutron stars. We're talking about magnetic fields 1,000 times more powerful. 1 trillion times more powerful than the strongest magnetic field ever created in a laboratory. 1 quadrillion times more powerful than Earth's magnetic field. The number is so large it becomes almost meaningless. 10 to the 15th Gauss, a 1 followed by 15 zeros. To put this in perspective, The Earth's magnetic field, the one that protects us from solar radiation and allows compasses to work, measures about half a Gauss. A typical refrigerator magnet is about 100 Gauss. The strongest continuous magnetic field ever created by humans in a laboratory reached about 45 Tesla, or 450,000 Gauss. The Sun's magnetic field, powerful enough to create solar flares and coronal mass ejections, reaches a few thousand Gauss in its most intense regions. Now, multiply that by 1 trillion. The physics community was skeptical, and for good reason. The energy required to generate and maintain such a magnetic field seemed impossible. The magnetic field itself would contain more energy than the neutron star's rotational kinetic energy. Where would that energy come from? How could it be sustained? It violated our understanding of dynamo theory, the process by which astronomical bodies generate magnetic fields. The math seemed sound, but the implications were so extreme that most astronomers filed the magnetar theory away as an interesting but unlikely possibility. Then the evidence started mounting. That burst in 1979, now designated SGR 052666, wasn't a one-time event. The source began producing smaller bursts at irregular intervals. Soft gamma-ray repeaters, they were called. SGRs. Objects that would periodically emit bursts of soft gamma rays and hard X-rays with no clear pattern. They couldn't be explained by any known astronomical phenomenon. They weren't supernovae. They weren't black holes. They weren't regular pulsars. Throughout the 1980s and early 1990s, more SGRs were discovered. Each one exhibited the same bizarre behavior. Short bursts of incredibly intense radiation, repeating at unpredictable intervals. Some would go silent for years, then suddenly erupt with dozens of bursts in a single day. The scientific community was forced to confront the possibility that Duncan and Thomson might be right. The breakthrough came in 1998 when another giant flare erupted from an SGR designated 1900-114. This explosion, while not as powerful as the 1979 event, was close enough and well observed enough that astronomers could study it in detail. The data confirmed what Duncan and Thomson had predicted. These weren't just neutron stars. These were neutron stars with magnetic fields so powerful they defied comprehension. The term magnetar was officially adopted, and the hunt was on to find more of these cosmic monsters. By the early 2000s, the magnetar theory had gone from fringe science to accepted fact. Astronomers now estimate that roughly 10% of all neutron stars are born as magnetars. Given that there are probably hundreds of millions of neutron stars in our galaxy alone, that means there could be tens of millions of magnetars lurking in the Milky Way. Most of them are dormant, their magnetic fields having decayed over millions of years. But some are still active, still capable of producing outbursts that could affect us from thousands of light years away. The physics of magnetars forces us to confront what matter can actually do under the most extreme conditions imaginable. When we talk about a magnetic field of 10 to the 15th Gauss, we're not just talking about a really strong magnet. We're talking about a fundamental warping of space, time, and matter itself. At these field strengths, quantum mechanics goes haywire. The vacuum of space, which we think of as empty, isn't actually empty. It's filled with what physicists call virtual particles, electron-positron pairs that pop in and out of existence on timescales, so short we can't directly observe them. Under normal conditions, these virtual particles don't affect anything. But in the magnetic field of a magnetar, the vacuum itself becomes polarized. These virtual particles are ripped apart before they can annihilate each other. The fabric of space-time becomes birefringent, meaning light can no longer travel in straight lines. Photons split into pairs. The universe, as we understand it, stops making sense. The surface of a magnetar is a hellscape beyond imagination. The temperature hovers around 10 million degrees Celsius. That's nearly as hot as the core of the sun, but this is just the surface. The crust is made of iron, but not iron as we know it. Under the immense pressure and magnetic field, iron atoms are crushed into a crystalline lattice so dense and so rigid that it makes diamond look like tissue paper. This crust is only about a kilometer thick, covering an interior that might contain exotic forms of matter that can't exist anywhere else in the universe. Superfluid neutrons, superconducting protons, possibly even quark matter, where neutrons themselves break down into their constituent quarks. The magnetic field emerging from this surface doesn't just affect nearby matter. It affects the structure of the magnetar itself. The field is so powerful that it distorts the shape of the star, creating mountains and valleys on its surface. But these aren't mountains in any sense we understand. They're perhaps a few millimeters tall, but given the density of the crust, those millimeter-high mountains represent unimaginable stresses on the structure of the star. Eventually, the crust can't take it anymore. The magnetic field shifts, the internal structure adjusts, and the crust cracks. This is called a starquake, and it's one of the most violent events in the universe that isn't a supernova or a gamma-ray burst. When the crust of a magnetar cracks, magnetic field lines that were trapped beneath the surface suddenly snap into new configurations. This releases energy. A lot of energy. In the space of 1/10 of a second, a magnetar starquake can release more energy than the sun produces in 100,000 years. This energy explodes outward as a burst of gamma rays and X-rays, traveling at the speed of light in all directions. If you were somehow watching from a safe distance, you would see the magnetar suddenly brighten by a factor of thousands, then fade back to its normal luminosity over the course of minutes or hours. From Earth, we detect these events as soft gamma repeaters, the bursts that first hinted at the existence of magnetars back in the 1970s. On December 27, 2004, astronomers detected the most powerful explosion ever recorded that wasn't a supernova or a gamma-ray burst. A magnetar designated SGR 1806-20, located 50,000 light-years away on the far side of the Milky Way, experienced a megaflare. In less than a second, this single neutron star released more energy than the sun will produce in 200,000 years. The gamma-ray burst was so intense that it ionized Earth's upper atmosphere, disrupting radio communications across the entire planet. Satellites were temporarily blinded. The night side of Earth, the side facing away from the source, detected the radiation that had bounced off the moon. This explosion happened 50,000 light-years away. To put that in perspective, that's halfway across the galaxy. The light from this event had been traveling since before humans developed agriculture, and when it finally reached us, it still had enough energy to affect our technology. Astronomers calculated that if this same magnetar had been located just 10 light-years from Earth, roughly twice the distance to the nearest star, the radiation would have triggered a mass extinction event. The ozone layer would have been stripped away. The surface of Earth would have been bathed in lethal doses of gamma radiation. Life as we know it would have been sterilized. And 10 light-years is nothing on a galactic scale. It's right next door. This is what makes magnetars so simultaneously fascinating and terrifying. They represent the absolute edge of what the universe is capable of creating. They're not theoretical, they're real. They're out there right now, scattered throughout our galaxy. And while the odds of one being close enough to harm us are astronomically small, they're not zero. We've identified roughly 30 confirmed magnetars so far, and we're constantly finding more. Every time we point a new X-ray telescope at the sky, there's a chance we'll discover another one. Some might be dormant, having exhausted their magnetic field energy millions of years ago. Others might be young and active, ticking time bombs waiting for their next starquake. The closest known magnetar to Earth is SGR 1806-20, the same one that produced the 2004 megaflare at 50,000 light-years. The next closest is perhaps half that distance. At these ranges, we're safe, but the galaxy is vast, and our census of magnetars is far from complete. There could be one lurking a few thousand light-years away that we simply haven't detected yet because it's been quiet for the past few centuries. Statistical models suggest there should be more magnetars than we've found, which raises an uncomfortable question. Where are they? Are they hiding in plain sight, masquerading as ordinary neutron stars? Or are they out there in the darkness between stars, waiting for the right moment to announce their presence with a burst of radiation powerful enough to light up our satellites? Let's talk about what would happen if you got too close to a magnetar. Not close enough to touch it, of course. That would be instantly fatal for reasons that have nothing to do with the magnetic field. We're talking about getting within a few thousand kilometers of one of these objects. At that range, something truly bizarre starts to happen. The magnetic field becomes so intense that it begins to affect the fundamental structure of atoms themselves. To understand this, we need to think about what atoms actually are. An atom consists of a nucleus, made of protons and neutrons, surrounded by a cloud of electrons. These electrons don't orbit the nucleus like planets orbit a star, despite what your high school textbook might have shown you. Instead, they exist in probability clouds, regions of space where they're likely to be found. The shape of these clouds determines how atoms bond with each other, how molecules form, and ultimately how chemistry works. In a normal magnetic field, even a very strong one, these electron clouds remain roughly spherical. But in the magnetic field of a magnetar, something extraordinary happens. At a distance of about 1,000 kilometers from the surface, the magnetic field reaches a critical threshold. At this point, the electron clouds begin to distort. They stretch out along the direction of the magnetic field lines, transforming from spheres into elongated cylinders. This might not sound like a big deal, but it fundamentally breaks chemistry as we know it. Atoms can no longer bond with each other in the normal ways. The strength and geometry of chemical bonds depends entirely on the shape of electron clouds. When those shapes change, everything changes. Move closer to about 600 miles from the surface, and things get even stranger. At this range, the magnetic field strength reaches about 10 to the 13th Gauss. This is the point of no return for molecular structure. The distortion of electron clouds becomes so severe that molecular bonds simply cease to function. If you were somehow at this distance, your body would stop being made of molecules. The proteins that make up your cells, the DNA that encodes your genetic information, the chemical reactions that keep you alive, all of it would simply stop working. You wouldn't die in any conventional sense because the chemical processes that define death couldn't occur. You would cease to exist as a coherent arrangement of matter. your atoms would still be there, but they would no longer be organized into the complex molecules that make up a living thing. You would, in the most literal sense possible, fall apart at the molecular level. This isn't speculation or exaggeration. This is what the physics tells us happens in magnetic fields of this strength. The electromagnetic force, one of the four fundamental forces of nature, is what holds molecules together. When you introduce a magnetic field powerful enough, it overwhelms those molecular bonds. The math is straightforward and terrifying. But the effects of a magnetar's magnetic field extend far beyond just disrupting chemistry. At these extreme field strengths, something even more fundamental starts to happen. The vacuum of space itself begins to behave in ways that seem impossible. In quantum field theory, what we call empty space isn't really empty. It's filled with quantum fields that permeate all of existence. Under normal conditions, these fields don't do much. They're there, contributing to things like the cosmological constant and dark energy, but they don't interact with matter in obvious ways. In the magnetic field of a magnetar, this changes. The quantum vacuum becomes polarized. Virtual particle pairs, electron-positron duos that normally pop in and out of existence too quickly to measure, are ripped apart before they can annihilate. The vacuum develops an effective index of refraction, like glass or water, but for the vacuum of space itself. This means that light can no longer travel in straight lines near a magnetar. Photons, the particles of light, begin to interact with the polarized vacuum. A single photon can split into two photons, or even into an electron-positron pair, through processes that simply don't occur anywhere else in the universe. The space around a magnetar becomes optically active, meaning it rotates the polarization of light passing through it. If you could somehow observe a magnetar up close with polarized sunglasses, you would see the light twisting and warping in ways that violate our everyday understanding of how light behaves. The implications of this are staggering. Near a magnetar, some of the most fundamental assumptions of physics break down. Light doesn't travel in straight lines. The eye's speed of light itself becomes direction dependent. Photons with different polarizations travel at slightly different speeds. This effect, called vacuum birefringence, has been predicted by quantum electrodynamics for decades, but magnetars are the only places in the universe where it becomes significant enough to observe. In 2016, astronomers finally detected vacuum birefringence in the light coming from a magnetar designated RX J8856 on 53754. This was the first direct observation of the quantum vacuum being polarized by a magnetic field, confirming predictions that had been made 70 years earlier. It was a triumph of theoretical physics and a reminder that the universe contains places where the laws of nature operate in ways we can barely comprehend. The surface of a magnetar exists in a regime of physics that we can calculate but never replicate. Our most powerful magnets, the ones used in particle accelerators and fusion reactors, reach maybe 45 Tesla. A magnetar's surface field is about 100 billion Tesla. We're not even close. We can't study this physics in a laboratory. We can only observe it from thousands of light years away and try to understand what we're seeing. The surface of a magnetar is a place of unimaginable extremes. The temperature is around 10 million degrees Celsius, hot enough that the iron atoms in the crust are completely ionized. Every electron has been stripped away, leaving bare nuclei surrounded by a sea of free electrons. This is called a plasma, and it's the same state of matter that exists in the cores of stars. But unlike the Sun, where the plasma is held together by gravity and pressure, the plasma on a magnetar's surface is held together by the magnetic field. The field is so strong that it dominates everything. Matter can't move perpendicular to the field lines. Charged particles, like the free electrons in the plasma, are forced to spiral along the field lines in tight helixes. The only motion allowed is along the field lines themselves. This creates a bizarre situation where the magnetar's surface isn't really a surface in the way we understand it. It's more like a series of magnetic field tubes, each one containing plasma that can only move in one dimension. These field tubes emerge from the star's interior, arc through space above the surface, and plunge back down somewhere else. Near the magnetic poles, where the field lines are most concentrated, the plasma is incredibly hot and dense. Near the magnetic equator, it's relatively cooler and more diffuse. This creates a temperature difference across the star's surface of millions of degrees over distances of just a few kilometers. The crust of a magnetar, despite being made of iron, is not like any iron that exists on Earth. Under the extreme pressure and magnetic field, the iron nuclei arrange themselves into a crystalline lattice with properties that border on the surreal. This lattice is so rigid that it makes diamond look like soft clay. The shear modulus, a measure of how resistant a material is to deformation, is about 10 to the 30th times greater than diamond. To put that in perspective, if you could somehow grab a cube of magnetar crust material 1 centimeter on a side, it would take more energy to bend it than the Sun produces in a year. This rigidity is important because it's what allows the crust to store the stress created by the magnetic field. As the magnetic field evolves and shifts over time, it creates enormous stresses in the crust. The field is trying to reconfigure itself into a lower energy state, but the crust resists. Energy builds up, like bending a steel bar further and further until it finally snaps. When the crust can no longer withstand the stress, it fractures. This is a starquake, and it's one of the most violent, non-explosive events in the universe. A starquake on a magnetar happens in a fraction of a second. The crust cracks along a fault line, just like an earthquake on Earth, but the scale and violence are incomparable. On Earth, the crust might move a few meters during a major earthquake. On a magnetar, the crust might shift by less than a millimeter. But remember, this is matter compressed to nuclear density. That millimeter of movement represents a change in the distribution of more mass than exists in Mount Everest. The crack propagates through the crust at close to the speed of sound in the material, which is about half the speed of light. As the crust shifts, the magnetic field lines that were anchored in the crust suddenly snap into new configurations. Field lines that were parallel are forced to cross each other, and when magnetic field lines cross, they can reconnect in a process that releases tremendous amounts of energy. This reconnection happens almost instantaneously. In the space of 1/10 of a second, the magnetic field dumps more energy into the magnetar's magnetosphere than the Sun will produce in 100,000 years. This energy goes into accelerating charged particles to nearly the speed of light and into producing an intense burst of gamma rays and X-rays that explodes outward in all directions. The 2004 megaflare from SGR 180620 released approximately 10 to the 46th joules of energy in less than a second. To put that in context, that's equivalent to about 1,000 supernovae going off simultaneously, except concentrated in a sphere only 20 kilometers across. The initial spike of the flare was so bright that it outshone everything else in the galaxy for a brief moment. detectors on satellites orbiting Earth were designed to measure X-rays and gamma rays from distant sources. They were not designed to handle a source this bright. Many of them simply saturated, their sensors overwhelmed by the flood of photons. It was like trying to measure the brightness of the sun with a night vision scope. The detectors just couldn't handle it. As the radiation from the megaflare raced outward at the speed of light, it created a shell of gamma rays and X-rays expanding at 300,000 kilometers per second. When this shell reached Earth, 8 minutes after the event began, it slammed into the upper atmosphere with enough energy to strip away a measurable fraction of the ionosphere. The ionosphere is a layer of Earth's atmosphere between about 60 and 1,000 kilometers altitude, where solar radiation has ionized the atoms, creating a layer of free electrons and ions. This layer reflects radio waves, which is why we can bounce radio signals around the curve of the Earth. When the Magnetars radiation hit, it ionized the atmosphere even more, changing the properties of the ionosphere and disrupting radio communications worldwide for several minutes. Instruments on the night side of Earth, the side facing away from the magnetar, detected the burst after it had bounced off the Moon. The Moon, which we think of as a dead rock with no atmosphere, actually has a tenuous exosphere and is constantly bombarded by solar radiation. When the Magnetars megaflare hit the Moon, it scattered off the lunar surface and some of it reached Earth. The fact that we could detect the burst that way tells you just how powerful it was. Astronomers who studied the data were able to calculate what would have happened if the magnetar had been closer. At a distance of 10 light-years, the radiation would have delivered a dose of about 8,000 times the normal background radiation level to anything on the surface of Earth. That's not instantly lethal, but it would be enough to significantly increase cancer rates and cause widespread radiation sickness. More importantly, it would have stripped away a significant portion of the ozone layer. The ozone layer is what protects us from the sun's ultraviolet radiation. Without it, the surface of Earth would be bathed in UV light at levels that would be lethal to most complex life. Plants would die. The food chain would collapse. It would be a mass extinction event on par with the asteroid that killed the dinosaurs, except it would happen in minutes instead of years. At a distance of 3,000 light-years, which is still quite far on a galactic scale, a magnetar megaflare would deliver radiation doses that would be immediately lethal. We're talking about hundreds of grays of radiation, enough to kill a human in hours or days. But the real killer wouldn't be the immediate radiation dose. It would be the long-term effects. The atmosphere would be chemically altered. The ozone layer would be destroyed. The climate would be thrown into chaos as the upper atmosphere's temperature spiked and then crashed. If we go closer still, to within a few hundred light-years, the radiation would be intense enough to sterilize the surface of any planet in the line of fire. We're not just talking about killing complex life. We're talking about destroying even the hardiest bacteria, the extremophiles that can survive in boiling acid or the vacuum of space. At these distances, a magnetar flare becomes an extinction-level threat not just to complex life, but to all life. Fortunately, the nearest known magnetar is 50,000 light-years away. At that distance, even a megaflare is just an interesting astronomical event, not a threat to our existence. But the keyword there is known. Our census of magnetars is far from complete. We've only identified about 30 of them, and statistical models suggest there should be tens of thousands of active ones in the galaxy and millions of dormant ones. The vast majority of these are too far away to detect unless they do something dramatic like produce a megaflare. What makes magnetars even more terrifying is that we can't predict when they'll erupt. Unlike pulsars, which sweep beams of radiation past Earth with clockwork regularity, magnetars are chaotic. Some produce regular small bursts every few days or weeks. Others stay silent for years, then suddenly erupt with dozens of bursts in a single day. Some have produced only a handful of bursts in the entire time we've been observing them. We don't know what triggers starquakes. We don't know why some magnetars are active while others are dormant. We don't even know for sure how many magnetars exist in our galaxy. Every number we have is an estimate based on extrapolating from the small sample we've found. The physics tells us that magnetars should be relatively rare, making up perhaps 10% of all neutron stars. But neutron stars themselves are rare, the remnants of only the most massive stars. In a galaxy of 400 billion stars, perhaps 1% will end their lives as neutron stars. That gives us maybe 4 billion neutron stars in the Milky Way. And if 10% of those are magnetars, we're looking at 400 million magnetars total. Most of them are old and dormant, their magnetic fields having decayed over millions of years. But some, perhaps 1% of the total, are still young and active. That's 4 million active magnetars in our galaxy right now. We've found 30 of them. The rest are out there, scattered throughout the spiral arms, most of them too far away or too faint to detect with current technology. To understand how a magnetar forms, we need to rewind to the beginning of the story, billions of years before the monster is born. It starts with a star, but not just any star. The progenitor of a magnetar must be massive, at least 40 times the mass of our Sun, perhaps even more. These stellar giants are rare. In a galaxy like the Milky Way, only about 1 in every million stars is massive enough to eventually become a magnetar. They burn hot and fast, fusing hydrogen into helium in their cores at rates that dwarf what happens in stars like the Sun. Where our Sun will live for 10 billion years, these massive stars exhaust their fuel in just a few million years. They're the shooting stars of cosmic timescales, blazing brilliantly and dying young. As these massive stars age, they begin fusing heavier and heavier elements. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Carbon and oxygen fuse into neon, magnesium, silicon. Each stage of fusion releases energy that supports the star against gravitational collapse, but each stage also produces less energy than the last, and burns through its fuel faster. By the time the star is fusing silicon into iron in its core, it has only days left to live. Iron is the end of the line. Fusing iron into heavier elements doesn't release energy, it consumes energy. When the core of a massive star turns to iron, the star's death warrant has been signed. The iron core grows until it reaches about 1.4 times the mass of the Sun, a threshold known as the Chandrasekhar limit. At this point, the quantum mechanical pressure that has been supporting the core against gravity can no longer do its job. The core collapses. Not slowly, not gradually, but catastrophically. In less than a second, a sphere of iron the size of Earth collapses down to a sphere 20 kilometers across. The matter becomes so dense that protons and electrons are crushed together, merging into neutrons and releasing a flood of neutrinos. The collapse happens so fast that the outer layers of the star don't have time to react. They're still falling inward when the core suddenly stops collapsing. having reached nuclear density. The infalling material slams into the rigid core and bounces. This rebound, combined with the outward pressure from the neutrino flux, drives a shockwave back up through the star. The shockwave rips through the stellar envelope, heating it to billions of degrees and blasting it into space. This is a supernova, one of the most energetic explosions in the universe. For a few weeks, a single dying star can outshine an entire galaxy of billions of stars. But the real story is what happens in the core during those first few milliseconds of collapse. When the core of a massive star collapses into a neutron star, it doesn't just shrink. It also spins up dramatically. This is due to conservation of angular momentum, the same principle that causes a figure skater to spin faster when they pull their arms in. The progenitor star might have been rotating once every few days or weeks. When its core collapses from Earth size to city size, that rotation rate increases by a factor of millions. A newly born neutron star might be spinning hundreds or even thousands of times per second. At the same time, the magnetic field of the progenitor star gets amplified. Stars have magnetic fields generated by the motion of a charged plasma in their interiors, a process called the dynamo effect. When the star's core collapses, the magnetic field lines are dragged inward and compressed along with everything else. The strength of a magnetic field is proportional to the density of the field lines, so compressing the field by a factor of billions can amplify it by a similar amount. A star with a surface magnetic field of a few thousand Gauss can produce a neutron star with a field of 1 trillion Gauss. But that's still not enough to make a magnetar. Something else has to happen. The key to creating a magnetar lies in what happens during those first few seconds after the neutron star forms. The core is incredibly hot, billions of degrees, hot enough that the neutrons themselves are in a superfluid state. The outer layers are convecting violently, with currents of neutron-rich matter rising and falling at a significant fraction of the speed of light. The neutron star is spinning at perhaps 1,000 times per second. These three factors, the rapid rotation, the violent convection, and the superfluid interior, can combine to create what's called an alpha-omega dynamo. This is a much more efficient version of the dynamo process that operates in normal stars. In just a few seconds, the alpha-omega dynamo can amplify the magnetic field from 1 trillion Gauss to 1 quadrillion Gauss. The exact mechanism is still debated, and the physics is fiendishly complicated, but computer simulations have shown that it can work under the right conditions. The problem is that those conditions seem to be quite rare. Only about 1 in 10 neutron stars appears to be born with the combination of rapid rotation and strong initial magnetic field needed to trigger the alpha-omega dynamo. This is why magnetars are so rare compared to ordinary neutron stars. Once the magnetar is born, it enters what we might call its adolescent phase. This is when it's most active and most dangerous. The magnetic field, which contains an enormous amount of energy, begins to evolve. Field lines twist and tangle. Internal currents create secondary magnetic structures. The crust, which is trying to maintain a rigid structure, is constantly stressed by the shifting magnetic field. This stress builds up over months or years until the crust can no longer take it. A fracture forms, a starquake occurs, and the magnetar produces its first burst of gamma rays and X-rays. This burst announces the magnetar's presence to the universe. It might be detected by satellites orbiting Earth, or by telescopes on other worlds scattered throughout the galaxy. Or it might go unnoticed. One more brief flash of radiation in a universe full of violent events. Over the following years and decades, the young magnetar continues to produce bursts at irregular intervals. Some bursts are small, barely above the background level of X-ray emission from the star itself. Others are enormous, releasing more energy in a fraction of a second than the Sun produces in a century. The pattern, if there is one, is chaotic. We call these objects soft gamma repeaters, or SGRs, and they represent magnetars in their most active phase. As the magnetar ages, its behavior begins to change. The magnetic field, while still unimaginably strong, gradually loses energy. This happens through several mechanisms. Magnetic field lines can reconnect, converting magnetic energy into heat and radiation. The field can interact with charged particles in the magnetosphere, accelerating them to high energies and carrying away energy as they spiral outward. Most importantly, the magnetic field exerts a torque on the star itself, gradually slowing its rotation. A young magnetar might spin with a period of 2 seconds, meaning it completes one rotation every 2 seconds. As it ages, that period increases. 5 seconds, 8 seconds, 12 seconds. The energy lost to rotational spin down is enormous. A magnetar might lose as much energy in 10,000 years as the Sun will produce over its entire 10 billion year lifetime. This energy goes into maintaining the magnetic field and producing the bursts that make magnetars detectable. As the magnetar spins down and the magnetic field decays, the rate of bursting decreases. The starquakes become less frequent. The bursts become less energetic. After about 10,000 years, the magnetar enters what we call a dormant phase. The magnetic field is still incredibly strong by any normal standard, perhaps a trillion Gauss, but it's no longer strong enough to produce frequent starquakes. The magnetar might go centuries or millennia between bursts. To an observer, it looks like an ordinary neutron star, quietly emitting X-rays from its hot surface and slowly spinning down. But dormancy is not necessarily permanent. One of the most surprising discoveries about magnetars is that some of them can suddenly wake up after being quiet for decades, or even centuries. In 2009, astronomers detected a burst of X-rays from an object designated SGR 0488-5729. Follow-up observations revealed that this was indeed a magnetar, but one with a puzzle. Its magnetic field, as measured by the rate at which it was spinning down, appeared to be quite weak for a magnetar. Only about 6 trillion Gauss, which is strong but not nearly as strong as the quadrillion Gauss monsters we associate with magnetars. Yet it was producing bursts that should have required a much stronger field. The leading explanation is that SGR 0418-5729 has a buried magnetic field. The field we measure on the surface is relatively weak, but beneath the crust, in the star's interior, there might be a much stronger field that occasionally breaks through and causes bursts. This suggests that there might be a population of dormant magnetars out there that look like ordinary neutron stars on the surface but harbor intense magnetic fields in their interiors, waiting for the right moment to erupt. If this is true, then our estimates of the magnetar population could be dramatically low. There might not be tens of thousands of active magnetars in the galaxy. There might be millions of dormant ones that could wake up at any time. The question of how many magnetars exist is more than just academic curiosity. It has profound implications for the history of life in the galaxy. If magnetar outbursts are common enough, and if some of them occur close enough to inhabited star systems, they could be a significant factor in the evolution of life. A magnetar flare from a few thousand light-years away might not cause an immediate extinction event, but it could increase mutation rates, disrupt ecosystems, and alter the course of evolution. Some scientists have speculated that magnetar flares might have played a role in some of Earth's past mass extinctions. The Ordovician extinction, about 450 million years ago, wiped out roughly 85% of marine species. The cause has never been definitively determined. Some evidence suggests a nearby gamma-ray burst might have been responsible. Could it have been a magnetar flare instead? We don't know. The geological record doesn't preserve evidence of radiation events with enough fidelity to distinguish between different types of cosmic explosions. But the possibility is there, lurking in the data like a ghost. The life cycle of a magnetar can be divided into several phases, each lasting different amounts of time. The birth phase, when the neutron star first forms and the magnetic field is amplified by the alpha-omega dynamo, lasts perhaps a few seconds. The active phase, when the magnetar is producing frequent bursts and spinning down rapidly, lasts about 10,000 years. The dormant phase, when bursting becomes infrequent and the magnetic field has largely decayed, can last millions or even billions of years. Eventually, the magnetar's magnetic field decays to the point where it's indistinguishable from an ordinary neutron star. At this point, after perhaps 10 million years, the magnetar has effectively died. It's just another neutron star, spinning slowly and emitting thermal radiation from its cooling surface. But even in death, a magnetar leaves traces. The elements created in the supernova that gave birth to it are scattered throughout space, eventually mixing with clouds of gas and dust to form new stars and planets. Some of those elements, particularly the heavy ones beyond iron, were created by the intense neutron flux during the collapse. Every atom of gold, platinum, or uranium in the universe was created in the death throes of a massive star, and some of them were created in the birth of magnetars. The distribution of magnetars in our galaxy tells us something about where massive stars form and die. Magnetars are found predominantly in the spiral arms of the Milky Way, where star formation is most active. This makes sense. Massive stars live fast and die young, so they don't have time to drift far from where they were born. We also find magnetars associated with supernova remnants, the expanding shells of gas and dust left over from the explosion. By studying these remnants, astronomers can estimate the age of the magnetar and learn about the properties of its progenitor star. One of the most famous examples is the magnetar 1e, 1048.1 SU Phi 937, which is located near the center of a supernova remnant in the constellation Carina. The remnant is about 2,000 years old, which means the magnetar is also about 2,000 years old. It's an infant by astronomical standards, still in its most active phase. Observations of this magnetar have revealed some surprising details about how young magnetars behave. It produces bursts at irregular intervals, sometimes going months without any activity, then suddenly producing a flurry of bursts over the course of a few days. The bursts themselves vary wildly in intensity, from barely detectable to powerful enough to be seen halfway across the galaxy. Another well-studied magnetar is SGR 1900+14, located about 20,000 light-years from Earth in the constellation Aquila. This magnetar produced a giant flare in August 1998 that was the most powerful astronomical event ever recorded at the time. The flare released about 10 to the 44th joules of energy in less than a second, equivalent to all the energy the Sun will produce over 2,000 years, compressed into a burst shorter than a human heartbeat. The initial spike of the flare was so intense that it saturated detectors on satellites throughout the solar system. Astronomers studying the data realized that the flare had come from SGR 1900+14, which had been known since the 1970s but had never produced anything this powerful. Follow-up observations revealed that the flare had heated the magnetar's surface to billions of degrees, causing it to glow brightly in X-rays for weeks afterward. The event also produced seismic waves that rang through the star like a bell, creating oscillations that could be detected in the X-ray emission. By studying these oscillations, astronomers were able to probe the interior structure of the magnetar, learning about the density and composition of its crust and core. The story of Magnetar 4U01422+61 illustrates another fascinating aspect of these objects. This magnetar, located about 13,000 light-years away in the constellation Cassiopeia, is surrounded by a disk of material. This is unusual. Neutron stars aren't supposed to have disks. When a massive star explodes in a supernova, it's thought to blow away all the nearby material, leaving the neutron star core isolated in space. But somehow, 4U-142+61 has accumulated a disk of gas and dust in orbit around it. The disk is small, only a few times the diameter of the magnetar itself, and it contains perhaps a tenth of the mass of the Moon. But it's there, glowing in infrared light as it's heated by radiation from the magnetar. Where did this disk come from? The most likely explanation is that it's debris from the supernova that somehow wasn't blown away, perhaps because it was in a dense clump that the shock wave couldn't fully disperse. Or perhaps the disk formed later, from material pulled off a companion star. We don't know for sure. What we do know is that the disk is gradually spiraling inward, falling onto the magnetar's surface at a rate of about a billionth of a solar mass per year. That might not sound like much, but it's enough to release a measurable amount of energy as the infalling material crashes into the star at a significant fraction of the speed of light. The population of known magnetars has grown steadily over the past few decades as our telescopes have become more sensitive and our understanding of what to look for has improved. Each new discovery adds to the puzzle, revealing new behaviors and new mysteries. Some magnetars, like Swift J1822.31606, have surprisingly weak magnetic fields for objects that produce magnetar-like bursts. Others, like 1E2259+586, have gone through periods of intense activity followed by years of complete silence. A few, like SGR 162741, have only been detected once, producing a flurry of bursts over a few weeks in 1998 and then vanishing from our instruments. Are these objects still active, just too faint for us to see? Or have they truly gone dormant, their brief outburst the last gasp of a dying magnetic field? We won't know unless they wake up again, and we happen to be watching when they do. The galaxy is vast, and magnetars are small. Finding them is like trying to spot fireflies in a forest at night. You only see them when they flash. Finding a magnetar is not easy. Unlike stars, which shine steadily for billions of years, magnetars are faint and unpredictable. They don't emit much visible light. Most of their radiation comes out in X-rays and gamma rays, wavelengths of light that are completely absorbed by Earth's atmosphere. To detect them, we need space-based telescopes equipped with specialized detectors that can pick up these high-energy photons. Even then, we're only seeing the tip of the iceberg. A magnetar that's dormant, not producing any bursts, might be completely invisible to our current instruments. Its thermal emission, the glow from its hot surface, might be too faint to detect beyond a few thousand light-years. This means our census of magnetars is heavily biased toward the active ones. the young, loud objects that periodically announce their presence with bursts of radiation. The quiet ones, the old, dormant magnetars that might make up 90% of the population, remain hidden in the darkness between the stars. We know they're out there. The math tells us they have to be. But finding them is another matter entirely. The hunt for magnetars accelerated in the late 1990s with the launch of several X-ray telescopes that could monitor large portions of the sky simultaneously. The Rossi X-ray Timing Explorer, launched in 1995, was particularly important. It was designed to study the timing of X-ray sources with unprecedented precision, measuring how the brightness of an object changed on timescales of microseconds. This made it ideal for studying neutron stars, including magnetars. When a magnetar produces a burst, the burst itself might last only a fraction of a second. But the X-ray emission from the star's heated surface can persist for hours or days. Our XTE could catch these afterglows and study them in detail. Between 1995 and its decommissioning in 2012, our XTE detected dozens of bursts from known magnetars and discovered several new ones. Each detection added to our understanding of how these objects behave. We learned that magnetar bursts come in different varieties. Some are short and intense, lasting less than a second but releasing enormous amounts of energy. Others are long and relatively weak, lasting several seconds but releasing less total energy. Some bursts are accompanied by changes in the magnetar's spin rate, suggesting that the starquake that triggered the burst also affected the star's rotation. Other bursts produce no detectable change in spin, implying that the crust shifted in a way that didn't alter the star's moment of inertia. Another crucial instrument in the hunt for magnetars has been the SWIFT satellite, launched in 2004. SWIFT was originally designed to study gamma-ray bursts, the most powerful explosions in the universe besides the Big Bang itself. Gamma-ray bursts are thought to be caused by the collapse of massive stars, or the merger of neutron stars, and they release more energy in a few seconds than the Sun will produce in its entire lifetime. SWIFT's job is to detect these bursts, quickly determine their location, and swivel its X-ray and optical telescopes to observe the afterglow before it fades. But SWIFT is also sensitive to the kinds of bursts that magnetars produce. Over the years, SWIFT has detected numerous magnetar outbursts, some from known sources and some from previously unknown magnetars. One of SWIFT's most important discoveries came in 2008, when it detected a burst from an object designated Swift J182316006. Follow-up observations revealed that this was a magnetar, but one with peculiar properties. Its magnetic field, as measured from its spin-down rate, was only about 2 trillion Gauss. That's strong by any normal standard, but it's much weaker than the quadrillion Gauss fields we associate with classical magnetars. Yet it was producing bursts that looked exactly like those from stronger field magnetars. This discovery challenged our understanding of what a magnetar is. It suggested that the surface magnetic field might not tell the whole story, that there might be much stronger fields buried beneath the crust that occasionally break through and cause bursts. The process of confirming that an object is a magnetar involves several steps. First, we need to detect it, usually through a burst of X-rays or gamma rays. This tells us where to look. Next, we use X-ray telescopes to measure the object's properties. The most important property is its spin period. Magnetars rotate slowly compared to most neutron stars. A typical radio pulsar might spin hundreds of times per second with a period of milliseconds. A magnetar typically has a period of several seconds. We also measure how rapidly the spin is slowing down. All neutron stars spin down over time as they lose rotational energy, but magnetars spin down much faster than ordinary pulsars. By measuring the spin period and the rate of spin down, we can calculate the strength of the magnetic field using the equations of electromagnetism. If that field is above about 1 trillion Gauss, and if the object produces magnetar-like bursts, we can be fairly confident we're looking at a magnetar. But there are edge cases that don't fit neatly into categories. Some objects have high magnetic fields but don't produce bursts. Others have relatively modest fields but exhibit burst behavior. Nature, as always, is more complicated than our classification schemes. One of the most thoroughly studied magnetars is 1E22590586, located about 10,000 light-years from Earth. This object was discovered in 1981 as a faint X-ray source, but its true nature wasn't understood until the late 1990s. In 2002, it entered an active phase, producing dozens of bursts over the course of several months. Astronomers studying the data noticed something interesting. The bursts weren't random. They seemed to cluster together in time, with periods of intense activity followed by periods of relative quiet. This suggested that the mechanism producing the bursts had some kind of memory, that a burst in one location could trigger additional bursts nearby or influence when the next burst would occur. Computer models of magnetar crusts have since confirmed this idea. When the crust cracks in one location, it alters the stress distribution across the entire star. This can either increase or decrease the likelihood of additional cracks forming. The result is a complex pattern of bursting that looks random on short timescales but has subtle correlations when analyzed over months or years. Another fascinating magnetar is 1E15407.05408, notable for producing both magnetar-like bursts and pulsar-like radio emission. This hybrid behavior was unexpected. Magnetars and radio pulsars were thought to be distinct types of objects with different physical properties. Magnetars were supposed to have such strong magnetic fields that they suppressed the formation of the magnetosphere structure needed to produce radio waves. But 1E1547.0548 somehow manages to do both. During its 2009 outburst, it produced hundreds of X-ray bursts while simultaneously emitting radio pulses with each rotation. This discovery forced astronomers to reconsider the relationship between magnetars and pulsars. Perhaps they're not as different as we thought. Perhaps magnetars are just pulsars with unusually strong magnetic fields, and the division between them is more gradual than we realized. Or perhaps 1E1547.05408 is a transitional object, caught in the process of evolving from an active magnetar into a more conventional pulsar as its magnetic field decays. The geographical distribution of magnetars in our galaxy provides clues about their origins and evolution. Most confirmed magnetars are located in or near the galactic plane, the flattened disk where most of the Milky Way's stars reside. This makes sense because massive stars, the progenitors of magnetars, are born in the disk and don't live long enough to wander far from their birthplaces. We also find magnetars associated with young supernova remnants, the expanding clouds of debris from stellar explosions. The association isn't perfect. Some magnetars are found in regions with no obvious supernova remnant, possibly because the remnant has already dissipated, or because the magnetar received a kick during its formation and has since wandered away from the explosion site. Neutron stars can be accelerated to speeds of hundreds of kilometers per second during a supernova, enough to carry them thousands of light-years from where they were born over the course of millions of years. but the general pattern is clear. Magnetars are found where massive stars die, in the spiral arms and star-forming regions of the galaxy. We've also begun detecting magnetars in other galaxies, though this is much more challenging. The nearest large galaxy to the Milky Way is Andromeda, located about 2.5 million light-years away. At that distance, even a bright magnetar is incredibly faint, and only the most powerful outbursts have any hope of being detected. In 2008, the Chandra X-ray Observatory detected a burst from a source in the Andromeda galaxy that looked like a magnetar. The burst lasted about 10 minutes and released roughly 10 to the 39 joules of energy. That's about 1,000th the energy of the giant flares from nearby magnetars, which tells you how much more difficult it is to study magnetars at intergalactic distances. Nevertheless, the detection proved that magnetars exist in other galaxies, which wasn't really in doubt but is nice to confirm. More interestingly, it gave astronomers a chance to study the magnetar population in a different galactic environment. Andromeda is broadly similar to the Milky Way, but there are differences in metallicity, star formation rate, and stellar population that might affect how magnetars form and evolve. In 2020, astronomers made a breakthrough discovery that connected magnetars to one of the biggest mysteries in modern astronomy. For more than a decade, radio telescopes had been detecting brief, intense bursts of radio waves coming from random directions in the sky. These fast radio bursts, or FRBs, lasted only milliseconds but released as much energy as the Sun produces in several days. The source of FRBs was unknown. Dozens of theories were proposed, ranging from evaporating black holes to alien signals, but none had definitive evidence. Then, on April 28, 2020, radio telescopes around the world detected a powerful FRB coming from within our own galaxy. The source was immediately identified as SGR 1935-2154, a known magnetar, located about 30,000 light-years from Earth. At the exact same time as the radio burst, X-ray telescopes detected a typical magnetar burst from the same object. This was the smoking gun. At least some FRBs, perhaps many or even most of them, are produced by magnetars. The discovery revolutionized our understanding of both phenomena. It suggested that the extragalactic FRBs that had been puzzling astronomers for years might be coming from magnetars in distant galaxies, their signals amplified by some mechanism we don't fully understand. It also raised new questions. Why do only some magnetar bursts produce radio emission? What determines whether a burst will be detectable as an FRB? And what about the repeating FRBs, the ones that produce multiple bursts from the same location? Are those coming from particularly active magnetars, or is something else going on? The mystery of repeating FRBs is particularly intriguing. Most FRBs are one-off events, detected once and never seen again. But a small fraction, perhaps 10 or 20%, repeat. The same location in the sky produces multiple bursts over days, weeks, or months. The first repeating FRB, discovered in 2016, has now produced hundreds of bursts. The intervals between bursts are irregular, ranging from minutes to months, with no obvious pattern. If these repeaters are magnetars, and the April 2020 detection strongly suggests they are, then they must be exceptionally active magnetars, producing bursts far more frequently than the magnetars in our own galaxy. This could mean they're very young, still in their first few thousand years of existence when bursting is most common. Or it could mean we've been unlucky in the Milky Way, that most magnetars are more active than the ones we happen to have nearby. The sample size is still too small to draw firm conclusions, But every new detection adds to the picture. As of 2024, we have detected hundreds of FRBs, and the rate of discovery is accelerating as new radio telescopes come online. Each one is a potential window into the behavior of magnetars in distant galaxies, giving us a census of these objects across cosmic time. The challenge of detecting magnetars is compounded by the fact that we can only observe the ones that are currently active or have been active recently. A dormant magnetar, one that hasn't produced a burst in centuries, is essentially invisible unless we happen to point an extremely sensitive X-ray telescope directly at it and detect the faint thermal glow from its surface. This has been done in a few cases. Several neutron stars with properties consistent with magnetars have been identified based purely on their high surface temperatures and slow spin rates, even though they've never been observed to burst. These objects might be dormant magnetars, their magnetic fields still strong enough to heat the crust, but no longer causing frequent starquakes. Or they might be some other type of neutron star entirely, a reminder that our classification schemes are based on limited observations of a small sample. The universe doesn't care about our categories. It will produce whatever combinations of properties physics allows, and we have to figure out how to make sense of what we see. One of the most persistent questions about magnetars is how many of them have gone completely undetected. Statistical arguments suggest that for every active magnetar we've found, there should be dozens or hundreds of dormant ones. If magnetars remain active for about 10,000 years, and if they live for millions of years after that as cooling neutron stars, then 99% of all magnetars that have ever existed are now dormant. In the Milky Way alone, there could be tens of millions of dead magnetars, indistinguishable from ordinary neutron stars except for their slightly stronger magnetic fields and perhaps higher surface temperatures. Some of these might occasionally wake up, producing a brief flurry of activity before falling back into dormancy. This would explain objects like SGR 0418 Hu 5729, which appeared out of nowhere in 2009, produced bursts for a few months, and then went quiet again. If reawakening is common, then the number of potentially dangerous magnetars in our neighborhood is much higher than the 30 or so active ones we've cataloged. Any one of them could wake up tomorrow and produce a giant flare. The odds of any individual magnetar doing so are low, but with tens of millions of potential candidates scattered throughout the galaxy, the cumulative probability starts to add up. The search for magnetars continues with every new generation of telescopes. NASA's Neutron Star Interior Composition Explorer, or NICER, installed on the International Space Station in 2017, is designed to study neutron stars in unprecedented detail. NICER can measure the X-ray emission from a neutron star, and by studying how that emission changes as the star rotates, create a map of the star's surface. This allows astronomers to identify hotspots created by magnetic field lines and to study how the temperature varies across the surface. For magnetars, this is invaluable. It lets us see the effects of the magnetic field directly, rather than inferring them from spin-down rates. Future X-ray missions, like the proposed Athena telescope that the European Space Agency hopes to launch in the 2030s, will be even more powerful. Athena will be able to detect faint magnetars at distances of tens of thousands of light-years, potentially doubling or tripling the known population. It will also be sensitive enough to study magnetars in nearby galaxies, giving us a much larger sample to work with. Every new detection is a piece of the puzzle, helping us understand how these objects form, how they evolve, and what role they play in the broader ecosystem of the galaxy. The discovery that magnetars can produce fast radio bursts fundamentally changed how we think about these objects. For years, FRBs were astronomy's most perplexing mystery. They were discovered almost by accident in 2007, when astronomers analyzing old data from the Parkes Radio Telescope in Australia found a brief spike of radio emission that shouldn't have been there. The burst lasted less than 5 milliseconds, but was extraordinarily bright, far brighter than anything that should exist in the radio sky. Initially, there was skepticism that it was even real. Radio telescopes pick up interference all the time, from cell phones, satellites, microwave ovens, anything that generates electromagnetic radiation. But this signal had properties that ruled out terrestrial interference. It was dispersed, meaning the different frequencies arrived at slightly different times, exactly what you'd expect from a signal that had traveled through the ionized gas between galaxies. The amount of dispersion indicated the source was billions of light-years away. Something out there had released as much radio energy in a few milliseconds as the sun produces across all wavelengths in an entire day. Over the following years, more FRBs were detected. Each one came from a different part of the sky. None of them repeated. This randomness made them incredibly difficult to study. By the time astronomers realized an FRB had been detected and calculated its position, hours or days had passed. When they pointed other telescopes at that location, there was nothing there. No afterglow, no host galaxy bright enough to identify. Nothing. The sources seemed to destroy themselves in the act of producing the burst, or they were so intrinsically faint that only the brief moment of the FRB made them visible. Theories proliferated. Maybe they were colliding neutron stars, merging in a cataclysmic event that produced the radio burst as a side effect. Maybe they were evaporating black holes releasing their final burst of Hawking radiation. Maybe they were signatures of cosmic strings, hypothetical defects in space-time left over from the Big Bang. Or maybe, as a few scientists half-jokingly suggested, they were alien signals. None of these explanations quite fit the data. The energy requirements were too high. The rate at which FRBs were being detected implied they were fairly common, happening thousands of times per day across the observable universe. Whatever was causing them had to be relatively abundant, not some rare cataclysmic event. Then, in 2016, everything changed. Astronomers detected an FRB that repeated. The source, designated FRB 1211-2, produced multiple bursts over several months from the exact same location in the sky. This immediately ruled out any model that required the source to be destroyed. Whatever was producing these bursts could do it multiple times. Better yet, the repeating nature allowed astronomers to study the source in detail. They used radio interferometry, a technique that combines signals from multiple telescopes to achieve much higher resolution, and pinpointed the source to a dwarf galaxy about 3 billion light-years away. Within that galaxy, the FRB source was located in a region of active star formation, surrounded by a persistent nebula of ionized gas. This environment was consistent with a young neutron star, possibly a magnetar. The pieces were starting to come together. If FRBs came from magnetars, it would explain their energy output. It would explain why they could repeat, since magnetars produce multiple bursts over their lifetimes. It would explain their association with star-forming regions, where massive stars die and leave neutron stars behind. But there was still no definitive proof. The smoking gun came on April 28, 2020. SGR 1935+2-154 is a magnetar located in the constellation Vulpecula, about 30,000 light-years from Earth. It had been discovered in 2014 based on its X-ray emission and was known to be an active magnetar, producing occasional bursts. On that April day, multiple radio telescopes around the world detected a powerful radio burst coming from its direction. At the exact same time, X-ray satellites detected a typical magnetar burst from SGR 1935+2154. The temporal coincidence was unmistakable. The radio burst and the X-ray burst were two different wavelengths of emission from the same event. This was the first time a magnetar had been caught producing a fast radio burst. The energy of the radio burst was lower than the extragalactic FRBs that had been detected previously, but that made sense given the source was in our own galaxy. If this burst had occurred in a galaxy 3 billion light-years away, it would have looked exactly like the FRBs astronomers had been puzzling over for more than a decade. The discovery was announced in several papers published simultaneously in the journal Nature. It was immediately recognized as a breakthrough. At least some FRBs, and possibly all of them, were produced by magnetars. The mechanism is still debated. The leading theory is that starquakes, the same events that produce X-ray bursts, can also generate bursts of radio emission under certain conditions. When the magnetar's crust cracks and the magnetic field lines snap into new configurations, they can accelerate charged particles to enormous energies. These particles then emit radio waves as they spiral along the magnetic field lines, creating a brief, intense pulse that propagates outward at the speed of light. But not all magnetar bursts produce detectable radio emission. Of the thousands of X-ray bursts that magnetars in our galaxy have produced over the years, only a handful have been associated with radio bursts. This suggests that the geometry has to be just right. Perhaps the radio emission is beamed, concentrated into a narrow cone that only rarely happens to point toward Earth. Or perhaps most starquakes simply don't accelerate particles to high enough energies to produce significant radio emission. The details are still being worked out, but the connection is now firmly established. Magnetars are FRB sources. This has profound implications for our understanding of both phenomena. It means that the thousands of FRBs detected from distant galaxies are signposts pointing to magnetars billions of light-years away. Each FRB is a brief glimpse of a magnetar in another galaxy, frozen in time by the light travel delay. An FRB from a galaxy 3 billion light-years away shows us what that magnetar was doing 3 billion years ago, when the universe was less than a third its current age. By studying FRBs across a range of distances, we can learn about the magnetar population throughout cosmic history. Were magnetars more common in the early universe when star formation rates were higher? Do they evolve differently in galaxies with different metallicities? These questions are now within reach. The connection between magnetars and FRBs also raises questions about other astronomical mysteries. Magnetars might be responsible for more than just FRBs. They might play a role in gamma-ray bursts, the most powerful explosions in the universe. Gamma-ray bursts come in two varieties. Short-duration bursts, lasting less than 2 seconds, are thought to be caused by colliding neutron stars. Long-duration bursts, lasting more than 2 seconds, are associated with supernovae and the collapse of massive stars. But there's a subset of long bursts that don't quite fit this picture. They're too bright, or their spectra are wrong, or they're not associated with any detectable supernova. Some astronomers have proposed that these anomalous bursts might come from magnetars. If a magnetar forms with an exceptionally strong magnetic field and begins spinning very rapidly, it could channel energy into a jet of particles and radiation that punches through the surrounding supernova debris. This jet would produce a gamma-ray burst, but one with properties slightly different from the standard model. The evidence is circumstantial but intriguing. If magnetars can produce both FRBs and gamma-ray bursts, they might be responsible for a significant fraction of the transient events we see in the sky. Another area where magnetars might play a role is gravitational wave astronomy. Since 2015, the LIGO and Virgo detectors have been observing gravitational waves, ripples in space-time caused by accelerating masses. Most detections have been from colliding black holes, with a few from colliding neutron stars. But gravitational wave detectors are sensitive to other sources as well. A rapidly rotating neutron star with a bumpy surface, for instance, would emit gravitational waves. The problem is that neutron stars are generally very smooth. The immense gravity tends to flatten any mountains or irregularities. But magnetars are different. The intense magnetic field can distort the shape of the star, creating mountains perhaps a few millimeters tall. Those might not sound like much, but for an object spinning several times per second and compressed to nuclear density, even millimeter-high mountains could generate detectable gravitational waves. So far, no gravitational waves from a magnetar have been confirmed, but the search is ongoing. If we do detect them, it would provide an entirely new way to study these objects. Gravitational waves carry information about the interior structure of the star, the density profile, the equation of state of nuclear matter, things that are impossible to measure any other way. The possibility of colliding magnetars is even more exciting. If two neutron stars can merge and produce gravitational waves, why not two magnetars? The event would be similar, but with some crucial differences. The intense magnetic fields would interact as the stars spiraled together, possibly producing bursts of electromagnetic radiation alongside the gravitational waves. The merger itself might produce a hypermassive magnetar, an object temporarily supported against collapse by rapid rotation and magnetic pressure. This hypermassive magnetar would live for seconds or minutes before collapsing into a black hole, and during that brief existence it might produce the most intense magnetic field in the history of the universe. Theoretical calculations suggest the field could reach 10 to the 16th or even 10 to the 17th Gauss, 100 times stronger than the strongest magnetars we've observed. The energy released during the collapse could power a gamma-ray burst, potentially explaining some of the most luminous and long-lived bursts ever detected. Again, this is theoretical. We've never observed a magnetar merger. But the universe is vast and old, and if it can happen, it probably has happened somewhere at some time. For all their power and mystery, magnetars are still just neutron stars. They obey the same physical laws as everything else. We can study them using the tools of physics, running computer simulations to model their interiors, calculating how magnetic fields evolve over time, predicting what bursts should look like at different wavelengths. The challenge is that magnetars operate in regimes where our understanding of physics becomes uncertain. At the densities found in neutron star cores, matter behaves in ways we can't replicate in any laboratory on Earth. Protons and neutrons might dissolve into a soup of quarks. The strong nuclear force which holds atomic nuclei together becomes dominant over all other forces. We can write down equations, but we don't know if those equations are correct because we have no way to test them. The only laboratory is nature itself, and magnetars are one of the few places where we can observe these extreme conditions. This is why magnetars are so valuable to physics, beyond just being fascinating objects in their own right. They're natural experiments, probing the boundaries of what matter can do. One question that magnetars force us to confront is whether there's a maximum magnetic field strength. Is a quadrillion Gauss the upper limit, or could even stronger fields exist? Theoretical calculations suggest there might be a limit imposed by quantum electrodynamics. When the magnetic field becomes strong enough, the energy density in the field itself approaches the energy density of matter. At that point, the vacuum can spontaneously create electron-positron pairs, which would drain energy from the field. This process sets a theoretical maximum called the Schwinger limit, which is about 10 to the 17th Gauss. No magnetar has been observed with a field anywhere near this strong, but that doesn't mean they don't exist. Perhaps they're rare, or perhaps they exist only briefly during the formation of the magnetar before decaying to more typical values. Or perhaps the Schwinger limit can be exceeded under certain conditions we don't understand. This is the frontier of physics, where theory meets observation, and neither has all the answers. The question of how dangerous magnetars are to life on Earth depends entirely on distance. At 50,000 light-years, even a megaflare is just an interesting light show in our instruments. At 10,000 light-years, a megaflare would be concerning but probably not catastrophic. The radiation would increase cancer rates and disrupt technology, but life would survive. At 1,000 light-years, we're entering the danger zone. A megaflare from this distance would deliver radiation doses high enough to cause mass casualties and environmental damage. The ozone layer would be partially destroyed. Crop failures and ecosystem collapse would follow. It wouldn't be an immediate extinction event, but it would be a civilization-altering disaster. At 100 light-years, a megaflare would be an extinction-level event. The surface of Earth would be sterilized. Even bacteria sheltered deep underground would struggle to survive the initial radiation pulse and the long-term environmental collapse that followed. The good news is that there are no known magnetars within 1,000 light-years of Earth. The nearest confirmed one is about 5,000 light-years away, far enough that even its most powerful outburst would be a minor inconvenience. But the key word there is confirmed. Our census of magnetars is incomplete, and there could be dormant ones much closer that we haven't detected yet. Statistical estimates suggest that a magnetar flare powerful enough to significantly affect Earth happens somewhere in the galaxy roughly once every few million years. The odds that one of those flares occurs close enough to harm us are much lower, perhaps one in every few 100 million years. For comparison, large asteroid impacts capable of causing mass extinctions happen about once every 100 million years. So magnetar flares are a real threat, but they're not something we need to lose sleep over. The universe has plenty of other ways to kill us that are far more likely. Still, the possibility exists. If a nearby star were to go supernova and form a magnetar within a few hundred light-years of Earth, and if that magnetar were to produce a giant flare during its active phase, and if Earth happened to be in the line of fire, it would be catastrophic. The odds of all those ifs lining up are vanishingly small, but they're not zero. This is the uncomfortable reality of living in a universe that contains magnetars. They're out there, scattered throughout the galaxy, each one a loaded gun that could go off at any moment. Most of them are pointed in safe directions. Most of them will never fire. But some will, and when they do, anything nearby will feel the consequences. Looking to the future, our understanding of magnetars will continue to evolve as we build more powerful telescopes and refine our theoretical models. The next generation of X-ray observatories, like Athena and Lynx, will be able to study magnetars in exquisite detail. They'll measure the shapes of their magnetospheres, map the distribution of hotspots on their surfaces, and track how their magnetic fields evolve over time. Radio telescopes, like the Square Kilometre Array, currently under construction, will detect FRBs at unprecedented rates, giving us a statistical sample large enough to draw firm conclusions about the magnetar population across cosmic history. Gravitational wave detectors are being upgraded to be more sensitive, increasing the chances that they'll catch the signal from a magnetar starquake or even a magnetar merger. Each new observation is a piece of the puzzle, slowly revealing the full picture of what magnetars are and how they fit into the broader story of stellar evolution. But beyond the science, there's something deeply humbling about magnetars. They represent the universe's capacity for extremes, the edge of what's physically possible within the laws of nature as we understand them. A magnetar is what happens when you take a star, compress it to the absolute limit, and spin it up to thousands of rotations per second, while amplifying its magnetic field to strengths that warp the fabric of space-time. It's matter pushed to the breaking point and beyond, held together only by the fundamental forces of nature operating at their maximum intensity. And yet, despite their power, magnetars are also fragile. They exist for only a brief moment on cosmic timescales, 10,000 years of activity, followed by millions of years of slow decay. They're the universe showing off, demonstrating what it can build when all the conditions align perfectly, knowing that the creation will be fleeting. In that sense, magnetars are a lot like us. We're also brief, improbable arrangements of matter, held together by forces we don't fully understand, burning brightly for a cosmically insignificant span of time before fading back into the darkness. The story of magnetars is ultimately a story about limits. The limit of how dense matter can become before it collapses into a black hole. The limit of how strong a magnetic field can be before quantum effects tear it apart. The limit of how much energy can be released in a fraction of a second without destroying the source. And, perhaps most importantly, the limit of human understanding when confronted with phenomena so extreme they seem to belong to science fiction rather than science fact. We've come a long way since that morning in March 1979, when satellites across the solar system went haywire and scientists scrambled to figure out what had happened. We now know that the burst came from a magnetar, an object that didn't even have a name back then. We've identified dozens more, studied their properties, connected them to fast radio bursts, and possibly to gamma-ray bursts and gravitational waves. We've calculated how close one would need to be to threaten Earth and determined that we're probably safe, at least for the foreseeable future. But there's still so much we don't know. Where exactly do magnetars fall on the spectrum between neutron stars and black holes? Can their magnetic fields exceed the Schwinger limit? What happens inside their cores where matter exists in states we can't replicate? How many are out there in the darkness, dormant and waiting? These are the questions that will drive magnetar research for decades to come. And as we answer them, new questions will emerge, as they always do in science. The universe is not a puzzle with a fixed number of pieces. It's an infinite fractal of mysteries, each one revealing new layers of complexity when examined closely enough. Magnetars are just one chapter in that story, but what a chapter they are. Objects so powerful they could kill you from 600 miles away just by existing. Stars that can release more energy in 1/10 of a second than our sun will produce in 100,000 years. Cosmic lighthouses beaming signals across billions of light years, announcing their presence to anyone with the technology to listen. They are, in the most literal sense, awesome. They inspire awe not just because they're powerful, but because they're real. They're not the invention of a science fiction writer trying to top the previous story. They're what nature produces when the rules are pushed to their absolute limit. And the truly terrifying, truly wonderful thing is that they're out there right now, spinning in the darkness between the stars, waiting for the next starquake that will light up the galaxy with a burst of radiation that travels at the speed of light, carrying with it a message written in the language of physics. A message that says, the universe is vast and violent and beautiful, and you are very, very small.